Okay, welcome to our first video for Unit 7. We're getting into differential equations now, which, if I'm going to be honest, differential equations are one of my favorite topics in calculus, because this is like really where the things we've been learning meets practical application. Differential equations is, to what I know, the most type of used or applied calculus that we have in the widest range of fields. So, for example, differential equations are used when you're talking about meteorology and predicting if it's going to rain, if there's going to be a hurricane, how big are the earthquakes going to be. That would be a differential equation, a very complicated differential equation. We're not going to get that far. If you're talking about biology and you're talking about population models, well, that's going to be a differential equation because you're talking about the rate of change of a population over time. You can also use this with physics. Well, everything in calculus you can use in physics, but this is a very clear physics example I'm thinking of with a, this is going to sound like a weird example, but I know it's something that people research. But if you take a spring and you want to figure out how is that spring oscillating, and how does it bounce, sort of, that would be a differential equation. They use that a lot with physics, and you also get it into engineering when you're talking about creating or designing certain structures that rely on springs for things. Don't ask me what those are, but I know they have them. I know springs are used in the construction of things. Where else do we see differential equations? Those are the big examples that come off the top of my head. I'll try to come up with some more that I can give to us in class. But what is a differential equation? What is this thing that I'm talking about? I talked about how we can use it, but a differential equation is just an equation that relates unknown functions and their derivatives. Okay, so what do I mean by that? Well, here's an example. I talked about population models. That's one of my favorites with differential equations. But let's talk about the rate of change of a population over time. So that rate of change over time, this is the rate that a population changes over time, dp over dt. And I'm going to give it a simple one. This is not a true. We'll call that e to the t. This is a differential equation. This is a very simple differential equation, but it is one nonetheless, where it's saying that the rate of change of the population with respect to time is e to the t. So this is, we've dealt with differential equations before, but we haven't solved them. We haven't solved differential equations, which is going to bring in that integration piece to us. And we're going to get to that later. But for right now, I just want us to focus on writing differential equations. And there's two pieces of information that we need for that. And the two pieces we need are variation, which maybe you learned about in Algebra 1, maybe you didn't. I would say you should have learned it in Algebra 1, but it's not something that I super teach in Algebra 1. So I know for me, if I were to have any of my freshmen, again, as seniors and they're taking me, they would not know what this is unless you've learned it in Algebra 2 or Pre-Cal or Geometry, which I don't think you do. So we're just going to really quickly talk about it. It's going to be very brief. It's not anything super substantial, but direct variation, if y varies directly as x, or if y is directly proportional to x, that just means that we are going to have a constant in there. So, and I'm going to call that constant k. So if we were to write an equation with direct variation, well, that's this equation right here. Y equals k times x. And this k actually is a fancy name. It's called the constant of proportionality. And I'm writing it on my thing. It's not something you're ever going to need to know. I'm never going to ask you to tell me to say this is the constant of proportionality, but just so you know what that's called. So if we're doing y varies directly as x or y is directly proportional to k, that means we're going to have some constant of proportionality in there, where y equals kx. And then inverse variation, y varies inversely as x or y is inversely proportional to k. Well, instead of this, it's k times x. This equation is just going to be y equals k divided by x. If we're inversely proportional, then we're going to dividing instead of multiplying. Okay, let's do some quick examples. 2 questions really quick, where we're going to write the equation, because that's going to be the first piece of this, is you're going to have to write your differential equation, and then you have to do stuff with it. And for right now, I'm just focusing on writing. So, bacteria in a certain culture increase at a rate proportional to the number present. A lot of information just in that one sentence. So it tells us that what we are talking about is bacteria. So one of our variables, or one of the things that we're talking about, is bacteria. So did it load? Sorry, I was waiting for it to load and it wasn't loading. There we go. So our bacteria. And then the next thing we have is that it increases at a rate. Rate is our key word. We've talked about this before. What does rate mean? Well, rate means it's our derivative. And it's increasing at a rate proportional. That means we're going to have our constant of proportionality. Sorry, I forgot to load it. Constant of proportionality to the number present. What color do I want? Let's do red. Number present. And this is also still talking about B, because it's talking about bacteria, to the number of bacteria present. That's implied. And I actually don't care about this question right here. We're going to get to that question later. I just want us to write the equation. So, bacteria in a certain culture increase at a rate proportional to the number present. The only other thing that I kind of want to note from this is it's talking about time. The number of bacteria doubles in 3 hours. How many hours? This is our kind of clue that it's talking about time. And time is always our dependent variable. So let's write this equation. We're talking about the derivative of bacteria with respect to time. So that's dB over dt is proportional to the number present. So proportional tells me I'm going to have k. It's directly proportional to the number of bacteria present. So I'm multiplying k times b. So this is relating relating our unknown function to its derivative. And our unknown function is b of t, just to be really clear. Unknown function is b of t. So we're relating, let me actually put that here too. And this is probably a more clear example. Our derivative is related to our function. We're relating these two things. That's what makes it a differential equation. Okay, and that's all I want us to do for now. If I remember, we'll come back to this and figure out what the actual answer to the question is. Let's come down here. Multiple choice is the last thing I'm going to say for this, for writing this equation. We're reading this question. A rumor spreads among a population of n people. So it gives us our variable n at a rate. Rate tells us what? It tells us we're looking at a derivative. Proportional, what does proportional tell us? Proportional tells us that we have a k to the product of, and now we're proportional to what? We're proportional to the product of the number of people who have heard the rumor and number of people who have not heard the rumor. And just another piece, P is the number of people who have heard the rumor. And we want something modeled with respect to time. Okay, I underline a lot of stuff. Hopefully it'll catch up. Okay. So first off, we're talking about our derivative of n with respect to time. So that means we're going to have dn over, or actually, I'm sorry. We're specifically talking about the number of people who have heard the rumor. So we're talking about the derivative of the people that have heard the rumor with respect to time. Because it's asking, we want the number of people that have heard the rumor. And we're relating these two things directly proportional. So that means we have k, our constant of proportionality. And what is that multiplied by? It's multiplied by the product of the number of people who have heard the rumor. So the number of people who have heard the rumor is P. And then we're multiplying that by the number of people who have not heard the rumor. Well, how do we find the number of people who have not heard the rumor? If this is all our people, this is n, and P people have heard the rumor, that's this amount here. How do we get this amount of people who have not heard the rumor? Well, this is just going to be n minus p, since n is bigger than p. And this is our number of people who have not heard the rumor, n minus p. And so we get this one. Which one matches? Well, that's going to be this one right here, B. And I know I said that was going to be my last example, but I actually think I want to do a couple more examples, at least a couple more examples here on this video instead of making a whole separate video since this one's kind of short. So let me get some more examples really quick. Okay, so I found 4 more examples that I want to do, and I do want to go through them kind of quickly. This first example right here, I want you to try and do it on your own. Go ahead and pause the video. When you come back, I'll have the answer. I'm going to talk through it, but I am going to talk through it kind of fast. Okay, so reading through this, I see my 2 variables are s and t. It tells me that in the first sentence. And as s increases, t decreases. That's sort of a clue that a certain type of proportionality is happening, but I won't say that yet. We're talking about a rate of change, so we're talking about a derivative, and it tells us we're talking about the derivative of s with respect to t, so that's ds over dt, is inversely proportional, so we're going to have our k over x to the natural logarithm of the quantity of t. So what is this going to end up being? It's going to be ds over dt equals, we're inversely proportional, so we're going to have our constant of proportionality on our numerator, to the natural logarithm of the quantity of t. So our denominator is going to be this ln of t. And there's our equation. Okay, next one. Go ahead and try it on your own. When I come back, I'll talk through it kind of quickly. Okay, and coming back, these are all the things that stood out to me. So we know we're talking about P of t, The population increases with respect to time at a rate. I should have included that in my brackets. Let me actually go back and include that. So that means dp over dt. That's our first part. That is directly proportional, so that means we're going to have k times x. Well, what is our x in this case? It says to the population, so kp. And this one actually takes us a step further. It gives us a little bit more information. I'm going to talk us through that information. It says, starting August 15th, the conditions were favorable and the population began increasing. On August 20th, 5 days later, there was an estimated 10 million insects. This gives us the information actually we need to find k. So let me dissect that information a little more closely with us all together. So So it says, on August 20th, 5 days later, there's an estimated 10 million insects. So that means P equals 10, because that's our population. And our population was increasing at a rate. What color do I want? This one. Increasing at a rate of 2 million per day, so that means dp over dt equals 2. Sorry. Well, actually, I don't need to be sorry because y'all can't see what I wrote because I haven't refreshed it yet. But I made a mistake, and that's all you need to know. And I fixed the mistake. That's also what you need to know. P equals 10. So when P equals 10, dp over dt equals 2. So now we have our P, we have our dp over dt, we can plug that in to find k. So we have 2 equals k times 10. That implies that k equals 1 over 5. That's a linear equation. I'm not going to go through solving that. And so our actual dp over dt equals 1 over 5 p. And we found our constant of proportionality to be 1/5. Okay. Third one. Again, try and go through it on your own, then we'll come back. Okay, so we've come back and we have that the rate of change of the volume of gas with respect to the pressure, so that's dV over dP, and that equals something direct, not directly proportional to the reciprocal. This is a new thing here. This is the same as inversely proportional to the reciprocal. So this is going to be our k over x. So we get k over, and what is our x? It's the square of the pressure. So that's p squared. And we get this differential equation right here. And I actually want to add a piece here that we haven't talked about. But what do we know about k? What can we figure out about k? So here, I added the piece that we actually found k. They don't give us the information to find k here. but we can say something about K. And the thing we can say is K going to be positive or negative? Well, if the pressure applied to a gas is increased while the gas is held at a constant temperature, the volume will decrease. So when pressure increases, volume decreases. So this rate right here should be negative. Because if P increases, and our function here, remember our function is our unknown function in this case, well, our unknown function's V of t, but two unknown functions, V of t and P of t. Or V of P, I suppose, actually. When our pressure, actually, yeah, I'm sorry, let me rephrase. Our unknown function here is V of P. Our volume with respect to the pressure, our volume pressure. So when pressure increases, volume decreases. So is this function going to be increasing or decreasing? Well, this function is decreasing. So our rate needs to be negative. So this K, this constant of proportionality, K must be negative. And that's the piece that we can add to say about K. Okay, last one, and I don't think I'm adding anything new here. Just kidding. Just kidding. Actually, I don't want to do this question yet because I'm going to add this question in our next unit. We're not going to do that one today. So that's the end of our intro to differential equations, and really we're just I'm gonna give you all time to practice in class on this for sure, but big ideas to take away. When we're writing our differential equation, we should have a derivative is equal to something, and it's going to be proportionally equivalent, whether it's inversely proportional, all those different wordings, you need to kind of learn what they mean. And then if it's talking about the square of the pressure, obviously it's pressure squared. If it's talking about the natural log of something, then, or natural logarithm, that's the natural log. So just sort of working on our reading comprehension and application, which I know is not the easiest. But thank you for watching.